Alright, welcome everybody. In the last video we talked about how to construct a scatter plot, which again is a way of visualizing the relationship between two variables. In this video we're going to talk about the common types of patterns that we can see in a scatter plot, what they might look like, and then also a little bit about the added value that scatter plots provide. So first, when we talk about correlations, both kind of in everyday language and in this course, most of what we're talking about are what are called linear correlations. So linear correlations, it's sort of implied by the name. Linear correlations are cases when variables are correlated, they're related to each other, but in a way that starts to approximate a straight line. So for example, a pretty strong linear correlation might look like this: amount of hours studied and the grade that is obtained on an exam. We wish the correlation was perhaps this strong. It's maybe not quite as strong, but we know that it's in the same upward direction. So linear correlations, they're related, and it's in a way that tends to form a straight line, especially as the correlation gets stronger. When we talk about calculating correlations in this course, and when we talk about using regression to make predictions, we're talking about linear relationships like this. So here are some of the common types of linear correlations. First, you might see linear correlations like the ones we just observed, where increases in one score and scores on one variable are linked to increases in scores on the other, and lower scores on one variable tends to be linked to lower scores on the other. These would all be called positive correlations. And here we see some scatter plots of some different strengths of positive correlations. First, this little guy R, we're going to learn a lot about R moving forward, but R is how we measure correlations. A perfect linear correlation looks like this on a scatter plot. Every single dot is on this straight line. There's some gaps in measurement there, but there's no deviation at all from that line. This is what's called a perfect positive correlation. Those basically never happen in reality except in very narrowly defined situations. Here's a strong positive linear correlation. We see again that same linear upward tendency, but again there's lots more fluctuation there. Lots of scores would be above or below that linear relationship if we drew it out. And then here we see fairly moderate positive correlation. They are positively correlated. That upward slope can be picked out, but there's a lot of noise, a lot of fluctuations among all those scores. So those are positive correlations. Next, we might see patterns that go in the opposite direction, where scoring higher on one variable is associated with scoring lower on the other. These are called negative linear correlations. You notice that the R's here are all negative numbers, and again, a perfect negative linear correlation makes a downward sloping straight line. There's no deviation from that line at all. A strong one, but not perfect. Again, it's a negative number. Again, you see that clear linear pattern, but there's lots of fluctuation there. And there's even more with the weaker correlation. Now, what do you suppose a zero correlation would look like? If two variables weren't correlated at all, what would their scatter plot look like? Well, I'll go ahead and show you. It's my job, I guess. So a no or null correlation is when two variables are essentially unrelated. You'll be pleased to know that the size of your toes has no relationship whatsoever with your grades, either on exams or overall. Those two variables, you can measure them, you can correlate them, but you're going to find that there is no consistent relationship there. Couple of things about null correlations. It's very rare for two variables to actually have exactly a zero correlation. It's probably going to come out at least a little positive or a little negative. A null correlation or a no correlation is generally one where we wouldn't reject the null in a hypothesis test. We're going to learn how to do hypothesis tests with correlations a couple videos down the line. And again, if it doesn't let us reject the null, we consider them uncorrelated. Another small note, this relationship here, toe size and grades, is a null correlation for adults, but for children it's actually positive correlation. You have a little thinking about why that might be the case for kids. Kids with bigger toes tend to score better on tests, and children with smaller toes tend to score worse. Think about why that might be the case for a bit. Either way, for adults, by the time we're all grown up, there is no correlation there. Now, once in a while, you will see data where the variables are clearly linked to each other. There is a relationship there, but it doesn't form a straight line. The relationship between the two kind of bends. It can form some kind of a curve. Here's an extreme example, and the data here is made up, but the relationship is real. There is a relationship between people's performance, both in exams and in places like work sites, and how much anxiety they're A moderate amount of anxiety actually tends to be associated with more performance. You focus, you're more kind of locked in, you're not getting distracted as much. You're oftentimes at your best when your anxiety level is moderate. But there is a tipping point there. When you get to a point when you're experiencing too much anxiety, you start to lock up, you get confused, you second guess yourself, you have trouble remembering things, you're so agitated that it's very difficult to think straight. So a high level of anxiety is worse than a moderate level. Notice these two variables are very closely linked to each other. There is a very clear pattern there, but it does not form a straight line. It forms a curve. Again, more anxiety is good up to a certain point, and then more anxiety becomes very, very bad. These curvilinear relationships are a little bit more advanced, a little more complicated. They're much harder to statistically assess, but you can still pick them out in a scatter plot. So here's the last thing about scatter plots. When we've talked about other ways of visualizing data way back when we were making tables and graphs and that fun stuff, generally we said, all right, this is just a way of making patterns a little more visually clear to a new observer or something. There's no real added value there. They don't really tell you anything that you couldn't get somewhere else with a different set of data, but they just kind of help you make sense of it. Scatter plots actually do provide unique information about the distribution of scores when we're correlating those two variables. Different patterns of data with totally different relationships can have similar or even identical correlations, and they can have similar or identical means. All the descriptive stats can look the same, but they can look very, very different on a scatter plot. So it's important to look at a scatter plot and not just look at those quantitative measures like your correlation, like your mean on each variable, because data can look very, very different. This leads to a little exercise I call Release the Data Source. Here's the idea of the data source. This is derived from a famous example from a century or two ago where a guy showed, hey, you can take totally different data sets. They can have the same average score on each variable, the same standard deviation for each variable, and the same correlation, but look very different. Well, these researchers use computer software to create a data source, which looks like this guy. Oh, this guy here. There's our data source. And also create different data sets that all have the same means on both variables, the same standard deviations on both variables, and the same correlation. I use advanced software to do this, but all of these different scatter plots you're looking at, and it starts to kind of choke on itself here for a minute, but it'll get back to normal. All those different distributions, those different scatter plots, would look exactly the same if all you knew were the means and standard deviations of each variable and the correlation between the two. Now we're back to a regular data source here. Look, again, after 2 decimal places, they're changing a little bit, but to 2 decimal places, these data sets are indistinguishable if all you knew were those different descriptive stats. But notice how different those patterns look. Again, it seems impossible. These look like very, very different sets of scores, but I assure you it's true. Again, the scatter plot is necessary to be able to tell the difference between these very different distributions of scores, because all the descriptive stats here look exactly the same. One of the neat things about scatter plots, they really do add extra value. It really is important to look at. All right, that's the end of this, and we will pick up next time by starting to talk about how we can quantify those correlations, how we can calculate what's called the correlation coefficient. All right, till then.